A set of positive integers is called fragrant if it contains at least two elements, and each of its elements has a prime factor in common with at least one of the other elements. Let P of n be n squared plus n plus 1. What is the least possible value of the positive integer b such that there exists a non-negative integer a, for which the set P of a plus 1, P of a plus 2, etc., up to P of a plus b is fragrant? In my video lessons, I take time to explain the solution of a math problem with maximum clarity. I try to present the concepts and ideas of the solution and avoid, wherever possible, using advanced mathematical notation that can be an obstacle for understanding the essence of the solution. Okay, first of all, let's rewrite this quadratic polynomial in the form n times n plus 1 plus 1. The first observation is that for any given natural number n, the value of this polynomial is always odd. This is because n and n plus 1 are two consecutive natural numbers. One of them is even, the other one is odd, so the product is even, and plus 1 is odd. And the second observation is that for any given natural n, the value of this polynomial is mutually prime with n plus 1. It's easy to prove if we assume that P of n and n plus 1 have a common factor, then 1 must also have that prime common factor, which is, of course, impossible. From that, it follows that the value of this quadratic polynomial for two consecutive natural numbers n and n plus 1 are also mutually prime. Indeed, if we write the formula for their difference, P of n plus 1 minus P of n, we see that it's equal to 2 times n plus 1. And we have just observed that the value P of n for any n is not divisible by 2 and is mutually prime with n plus 1. So the two values P of n and P of n plus 1 are always mutually prime. Thus, we have proved that number b, defined in this problem as the length of a sequence Pn plus 1, etc., cannot be equal to 2, because it's impossible that it has a subsequence of two adjacent numbers, a1 and a2, that have a common prime factor. From this, it follows that b cannot be equal to 3 either, because a1 and a2 cannot be adjacent in this sequence arranged in the same order as their corresponding arguments, and b1 between them cannot have a common prime factor with a1 or a2, and so this set of three members is not fragrant. If we assume that length b of our sequence is 4, then we must consider this sequence a1, b1, a2, b2 of values of our quadratic polynomial, in which a1 and a2 have a common prime factor, b1 and b2 have a different common prime factor. While a1 and b1 are mutually prime, b1 and a2 are mutually prime, and a2 and b2 are mutually prime. In this sequence, both pairs a1, a2 and b1, b2 can be written in the form P of a and P of a plus 2. And if we assume that such pair has a common prime factor, then the difference P of a plus 2 minus P of a must have the same prime factor. If we plug a and a plus 2 into the formula of this quadratic polynomial and simplify this expression, then simple algebra gives us that this difference results in the expression 2 times 2a plus 3. Since we know that the value of polynomial P of a and P of a plus 2 is odd, their common factor must also be odd. That's why the expression 2a plus 3 must be multiple of that common factor. We will denote this common factor by small letter p. Then, by following the rules of modular arithmetic and modular algebra, we can rewrite it as a is congruent to p minus 3 over 2 modulo p. Note that we can safely divide both sides of this modular equation by 2 because 2 is mutually prime with b. If we plug this expression for a into the formula for our quadratic polynomial, we will get that the quadratic polynomial p squared minus 4p plus 7 is congruent to 0 mod p. It's obvious that such modular equation can be satisfied only if this prime number p equals 7. So we have proved a little theorem that can be stated as this. The value of polynomial p of a and p of a plus 2 can have a common prime factor if and only if this prime factor equals 7 and a is congruent to 2 modulo 7 and thus can be written as 7 times some integer number plus 2. From this it follows that such sequence cannot exist because each pair a1, a2 and b1, b2 must have the same common prime number 7, which is impossible as we have proved earlier. Let's try to answer the question if the length of the sequence of the values of our quadratic polynomial can be 5. We have proved that the sequence a1, b1, a2, b2 is not possible, and to avoid it, we must insert one more member of the sequence, c1. We must insert it, for example, between a2 and b2 to avoid the sequence we had before. So now, in the new sequence, the distance between a1 and a2 is 2, and we know that its common prime factor must be 7, but the distance between b2 and b1 is now 3. Also, we know that c1 cannot have a prime common factor with either a2 or b2. Also, c1 cannot have a common prime factor with b1, because in this case, this common factor will also be 7. In which case a1 and b1, two adjacent members, will have a common prime factor 7, which is impossible. So c1 can only have a prime common factor with a1. And then the distance between a1 and c1 is also 3. And let's examine this case, when pa and pa plus 3 have a prime common factor. If we plug in a and a plus 3 into polynomial and simplify the expression for their difference, we'll have as the result the expression 6 times a plus 2. We know that the value of our polynomial is always odd. So if p of a plus 3 and p of a have a common prime factor, this prime factor can be either 3 or a factor of a plus 2. We can prove that a plus 2 cannot be divisible by any prime factor other than 3. If we assume that a plus 2 is congruent to 0 mod p and p is not equal to 3, then a is congruent to p minus 2 mod p. And if we plug in this expression into our polynomial and simplify it, we will have that p squared minus 3p plus 3 is congruent to 0 mod p. Obviously, it's possible only if p equals 3, which proves that the values of polynomial pa and pa plus 3 have only one common factor that's equal to 3. From this, it follows that two adjacent numbers c1 and b2 in the sequence that we are considering must both have common prime factor 3, which we know is not possible. This means that the length of a sequence that satisfies the requirements of this problem cannot be 5. Let's see if a converse of this theorem is also true. Suppose that the value of our quadratic polynomial is divisible by 3. We can write it in the modular form. A squared plus a plus 1 is congruent to 0 mod 3. Then we can subtract 3a from the left-hand side, because 3a is divisible by 3, which will give us the modular equation a minus 1 squared is congruent to 0 mod 3, and a minus 1 is congruent to 0 mod 3, which is equivalent to a is congruent to 1 mod 3. So the formula for argument A that satisfies this equation is 3 times any integer plus 1. So we have proved another little theorem that the values of polynomial p of a and p of a plus 3 have a common prime factor if and only if this common prime factor equals 3 and a is 3 times n plus 1. Next, let's try a sequence whose length is 6. Clearly, the 6 members of such sequence must consist of 3 pairs, A1, A2, B1, B2, C1, C2, in which, for example, the distance between B1 and B2 is 2, so their common factor must be 7. The distance between numbers A1 and A2 is 3, so their common factor must be 3. And the distance between C1 and C2 is 4. We can examine the case of two polynomial values, p of a and p of a plus 4, which must have a common prime factor. And if we use the same logic and method that we used for the case when p of a and p of a plus 2 have a common prime factor, we will obtain the result that such case is possible if and only if this common factor is 19 and number a has the form 19 times n plus 7. To finish this problem solution, we must find 3 consecutive numbers, a1, c1, and b1, such that the first one has residue 1 modulo 3, the second one has residue 7 modulo 19, and the third one has residue 2 modulo 7. We can find, for example, C1 from modular equations. C1 is congruent to 7 mod 19, and C1 is congruent to 2 mod 3, and C1 is congruent to 1 mod 7. By the Chinese remainder theorem, this number exists and it's unique in the interval from 1 to 399. Which is the product of 3, 7, and 19. This value of C1 equals 197. Then C1 minus 1 equals 196, is then congruent to 1 mod 3, and number 198 is congruent to 2 mod 7, as it should be. So the answer to the question of this problem is B equals 6. As a bonus, if we add number 399, which is the product of these 3 prime numbers, 3, 7, and 19, or any multiple of 399, to each of our 6 consecutive numbers, then the result will be another sequence of 6 consecutive numbers, which will have the same residues modular 3, 19, and 7, respectively.